All right, we are at the top of the hour, so I'm going to get us started. Hello, everybody. Welcome to today's webinar. If you've been following along with our materials analysis webinar series this year, you are going to remember that we tackled reverse engineering with FTIR in early February. Then earlier this month, we had a session dedicated to improving additive manufacturing qualification with X-ray microscopy. Today, we are going to continue our journey towards improving our materials analysis expertise. And we'll be doing this with the help of our partner, Frontier Labs, as we explore the topic of deformulation and failure analysis of polymers using Pyrolysis-GC. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be your moderator for today's event. I want to give a quick note about quantum analytics since before I introduce our speakers. We are a value-added distributor of analytical instrumentation in the United States and Canada. We offer equipment financing combined with technical services like cross-platform installation, training, and product support. For over 30 years, our company has helped researchers, scientists, and chemists get the best-in-class instrumentation they need, combined with technical services that help labs maximize their uptime. We offer solutions for a variety of applications, including gas chromatography, liquid chromatography, mass spec, organic and inorganic elemental analysis, TOC analysis, XRD, XRF, infrared, near infrared, and Raman spectroscopy, plus a whole range of sample introduction and preparation instrumentation to help extend the value of GCs and GCMS systems, like Mark's thermal desorption and Frontier pyrolysis solutions. And today, we are going to focus on the Frontier pyrolysis solution. Today's webinar is going to feature two presenters, Rogine Belganet and Athena Nguyen of Frontier Lab Americas. Rogine is the technical director. She started her profession as an analytical chemist working with various analytical instruments and techniques, such as pyrolysis-GC, TGA, FTIR, and X-ray, for material characterization, polymer identification, and contamination analysis. Athena Nguyen is the technical support specialist for Frontier Lab Americas. She has an extensive background in qualitative and quantitative analysis of organic compounds and polymer materials. Before I turn it over to our first speaker, I want to review a few housekeeping items. As a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available. This webinar, including Q&A, will last about an hour. Type your questions at any time into the question module in the webinar control panel. Rogine and Athena will be answering questions at the end of the webinar. Well, that ends our introduction, so without further delay, let's get started. Rogine, take it away.
Thank you very much, Lauren, for the nice introduction. All right. So before I also start going over the technical slides, let me start with a brief history about Frontier Labs. We were founded in 1991 by Dr. Chu Watanabe, also known as Chu-san. So Dr. Watanabe, with the support of some of the polymer scientists at Nagoya University in Japan, developed a pyrolyzer based on a vertical microfurnace design. We are a global corporation, and our main products are a series of pyrolyzers, such as the multifunctional and also the single-shot pyrolyzers, rapid screening reactors for catalyst analysis, and also a line of ultra-alloy stainless steel capillary columns. So here is our agenda for today's event. We first briefly go over the modern-day pyrolysis-GC using the microfurnace pyrolyzer and how you can really expand your material characterization capabilities by this technique. Then we will discuss the microfurnace pyrolyzer and its modes of operation. And then after that, one of our application chemists, as Lauren mentioned, Athena from our laboratory, will explain how easy and straightforward the sample preparation is, as well as where you can use this technique. Lastly, I will cover a couple of application notes to really show how the microfurnace pyrolysis-GC is used for material characterization of polymers and additives. So a very common question that we get is, what is pyrolysis? By definition, pyrolysis is a thermochemical decomposition of organic compounds at elevated temperatures without the participation of oxygen. Typically, you use an inert gas such as helium, and you apply a sufficient amount of heat to break down the organic bonds of a complex mixture into more stable and stable molecules referred to as pyrolysates. Now, these pyrolysates formed and their relative intensities provide insight into the nature of the original composition of your sample. It's very important to mention that applying the sufficient amount of heat and identifying the appropriate temperature to program your pyrolyzer furnace are critical factors in pyrolysis technique. And as we go more into detail from today's slide, you'll find out how to identify that sufficient amount of heat for your sample so you're not doing over pyrolysis or under pyrolysis of your samples. Now, what is pyrolysis-GC technique? Pyrolysis-GC is actually a very powerful and a straightforward technique that utilizes the microfurnace multifunctional pyrolyzer as a programmable temperature inlet to a gas chromatography mass spectrometer, GCMS system. Although I want to point out that you could use other detector depending on your application, for example, FID or NPD. And one of the application note that I will cover actually shows using pyrolysis, GCMS, FID, and NPD as well. So the microfurnace pyrolyzer is directly connected to your GC injection port. The sample is placed in a small deactivated cup, which then in return is positioned in a microfurnace. And then the temperature of the sample is precisely controlled to within plus or minus 0.1 degrees Celsius of the set furnace temperature to ensure that your sample-to-sample thermal profile is identical. So it's going to be a consistent one-step continuous pyrolysis using the microfurnace. Now, using this technology, the sample is maintained at ambient temperature in an inert atmosphere prior to pyrolysis. So eliminating any chance of evaporation, thermal degradation, or thermal setting of your sample before the analysis. And as I mentioned, that's a single-step pyrolysis, which means all the pyrolysates as they're generated directly and continuously will be deposited on your GC column in a single step. No transfer line, no switching valve, and no chemical trap. So let's now discuss a little bit about what are the advantages of microfurnace, or why would you want to add the microfurnace multifunctional pyrolyzer to your GCMS? And really the short answer to it is because you want to expand the capability of your GCMS system. As you can see here, substances at ambient temperature could be gas, liquid, or solids, mostly depending on their molecular weight. Materials that are soluble in solvents can be analyzed by instrumentation such as GC or LC. Of these compounds, about 30% can be analyzed by GC and about 80 to 85% by LC. But the key point here is you would need to have a proper solvent. However, as we all know in a laboratory, there are also some insoluble solid compounds that cannot be analyzed using your LC, LCMS, GC, or GCMS instrumentation. But this insoluble material can be analyzed by pyrolysis-GCMS. In fact, when you use pyrolysis-GCMS, a solid sample can be analyzed as is, and there is no need for performing any sample preparation or pretreatment, such as solvent extraction before your analysis. So the entire range of organic compounds, from gases all the way to the solids that are even insoluble in a solvent, can be analyzed by pyrolysis-GCMS. And that's really one of the advantages of the multi-mode pyrolyzer and how it can expand the capability of your GCMS instrumentation. So now, as the name says, we call this a multifunctional pyrolyzer, a multi-mode microfurnace, because it's not a traditional pyrolyzer where you could only perform flash pyrolysis. Actually, using the multifunctional pyrolyzer, you can perform multiple analytical techniques in addition to flash pyrolysis, both isothermal or temperature program. And these techniques or modes of operations could be evolved gas analysis, EGA, thermal desorption, double shot, hard cutting, reactive pyrolysis, and also UV radiation. So to chemically characterize your sample using the modern-day Pyrolysis-GC method. So if you are obtaining a sample, if someone is providing you guys a sample in the lab and say, what's in it? Is it additives, polymers? Can you identify the chemical composition of it? The first mode of operation that you want to perform is evolved gas analysis, EGA. And that's really a method map that we created for material characterization. And that method map provides you with two simple steps. And as I just mentioned, the first step will be running your evolved gas analysis, EGA. And think of EGA as something that it's a thermal separation, first of all, and that gives you a clear picture about the thermal profile and complexity of your sample. Now, the second step is to use the EGA thermogram that you just obtained and define the thermal zones of interest. So EGA really guides you on what to do next. It will show if a thermal desorption, double shot, hard cutting, flash pyrolysis is needed, or maybe even a combination of this technique is required for you. But again, the key point here is your evolved gas analysis mode of operation will be the first mode that you need to program your furnace for. So here is a summary of the analytical flow diagram for material characterization of unknown samples by showing an example. As you can see on the top, I'm showing an EGA thermogram of an eyeliner, a cosmetic eyeliner that we programmed the furnace from 40 to 500 C, and you see about 5 peaks or zone from your EGA thermogram. So again, EGA is the first step, and that provides us with the thermal profile and complexity of our sample. Now, we use our EGA thermogram to identify the thermal zones of interest. So if we decide to perform a flash pyrolysis or single shot that is shown all the way on the left-hand side, that's a fundamental technique typically for polymer analysis. And you obtain one pyrogram that indicates all the features of the sample. So in this specific example, all the compounds from those 5 peaks of your EGA, all the additives, all the breakdown of your polymer will show up in your pyrogram of a flash pyrolysis, or we also call it a single shot. So as you can imagine, this could make the interpretation challenging, especially if you're going after a, say, reactive monomer, that reactive monomer could be the breakdown of your polymer as well as an unreacted or raw monomer. So if you're trying to quantify that, you won't know if that, for example, say a styrene monomer peak that you're seeing from your pyrogram, is it the breakdown of your polymer, or is it a really unreacted raw monomer that you're trying to quantify? So to solve this, to solve this challenge, you could use a double shot mode, which is the combined analysis of your thermal desorption followed by flash pyrolysis. And I want to mention that this is just a one-time sampling. So you prepare your sample, you place it into the cup, and you program your furnace. Say in this case, I will do 40 to 300 C. Then I would obtain a thermal desorption chromatogram that shows as the first one. So all the additives and all those light volatile compounds will be thermally extracted from the sample. And then once your GCMS is running, once it's collecting all the data, your cup goes back up in an ambient temperature. So you're not exposing your cup and your sample to any heat in between the runs. Once it's done, and since your furnace then programmed for the next step, which in this case I would say 500 C, once the furnace is set at 500 C, the cup falls again back to the furnace to perform the second analysis on your sample. Now in a hard cutting mode, so if you want to perform a lot more detailed analysis, and that shows on the right-hand side. With the hard cutting mode, the EGA thermogram can be sliced into multiple temperature zones, and you actually obtain separate GCMS chromatogram for each of those zones. So instead of having all those first 3 peaks of additive in one chromatogram, just like a double shot, as I just mentioned, with hard cutting, you can now thermally slice your EGA into individual temperature zones. I would say one will be from 40 to 120, and then 120 to 200, 200 to 300, and that way you're only getting the GCMS chromatograms for those compounds that are evolving from those specific temperature zones. As you can imagine, this is actually a very powerful technique for performing competitive deformulation, reverse engineering, or even contamination and comparison analysis. And today, after Atina's talk, I will show a couple of application notes that how hard cutting is really provide a lot more detailed information than if you would perform single shot or a double shot analysis. So for right now, I'm gonna give the mic to Atina. She's gonna talk a little bit about her experience with the sample preparation. And I'm really excited for her to joining us today because previously she was a GCMS user, but she did not have the pyrolyzer. So when she joined Frontier, now she can actually really express her feelings and how appreciative she is with the pyrolyzer to be able to have a simple and a straightforward sample preparation by adding the pyrolyzer to the GCMS system. So Atina, I would like to give the mic to you, and once you're done, I'll go ahead and cover the application notes.
Thank you, Rosine. Hello everyone. My name is Atina. I am a technical support specialist of Frontier Lab. I started my position in January 2020, and I would like to share with you my experience with material characterization using Pyrolysis-GC. We will be discussing about the multi-mode pyrolyzer as the sample introduction technique. In Pyrolysis-GC technique, sample preparation is quick and simple. Depending on the sample types, we can decide to use the appropriate sampling tools such as a knife, microsyringe, micropuncher. A small amount of samples, about 1 to 200 micrograms, is inserted into the sample cup and ready for the analysis. There is almost no sample preparation needed or no solvent extraction is required. Here are some special tools which I frequently use to handle small samples for sample preparation in Pyrolysis-GC. The toolbox includes the micropuncher with 7 sizes from 0.5 millimeter to 5 millimeter. They are good for thin dry films. Laser blades, X-acto knives, metal file, tweezers, and pins are all handy. To demonstrate how easy and quickly sample preparation steps are done in Pyrolysis-GC, I would like to show 7 samples which I received earlier last year and analyzed in the lab. The 7 samples are in liquid form. Some of them are translucent liquid. So first of all, I took 7 samples and placed them on a hot plate at 70 degrees Celsius to dry out the moisture. Pictures so below are the sample before and after drying. After that, I used a syringe needle to pick up a small amount of sample, about 200 micrograms, inserted into the sample cup, and the analysis was then ready. One more sample that I would like to share is the analysis of the auto samples. I received 2 solid white pellet samples. One is auto stent pellets, and the other one is typical normal pellets. This is a comparison analysis between 2 samples. In order to analyze the smell in the samples, I decided to use the magic chemisorber PEG. It is a solid phase extraction element that uses polyethylene glycol as the stationary phase for high selectivity toward polar compounds. Picture is so below. The reason I used magic chemisorber PEG was because I wanted to extract all the smell from my samples. And the MGPEG allows me to perform a headspace analysis on solid samples. But also keep in mind that you could also use it for other sampling methods, such as direct immersion in liquid phase or gas sampling. Thermal resorption GC analysis is then performed using multi-mode pyrolyzer. One more thing I would like to mention about magic chemisorber PEG is that it can be reused immediately for the next sample run because it is usually cleaned automatically during the GC analysis. So back to my sample preparation. First of all, I attach the MGPEG onto the top of the eco stick and place it above the samples in the sample vial as shown in the picture. They were left for about 12 hours to extract all the smell. After that, The eco-stick was attached onto the double shot sampler. The double shot sampler was then attached into the furnace and ready for thermal desorption analysis. In this specific application, I use manual injection. However, there is an auto sort sampler which can automate up to 48 samples that you could also use. As a chemist in the lab, I enjoy sample preparation steps in pyrolysis-GC MS techniques very much because solid samples can be analyzed at ease. No solvent extraction is required. It is safe for the environment, and the analysis time is faster as a result. I am using Abstract to analyze the data obtained. I found that Abstract is an excellent tool for data interpretation, and here are the reasons. The Abstract system consists of just software and 4 Unix libraries, which allow me to select among the libraries for specific purposes. I can use Polymer EGA MS library, Polymer Py-GC MS library for integrated sum and find out the expected polymer in my samples. I can also use additive MS library, Polymer Pyrolysis MS library to integrate individual pix by pix and find out the compound names, its structures, and the corresponding polymer. I like how Abstract provides information suggestion on the original polymer of the compounds, where it might come from, and by comparing data obtained from different methods, the reliability of the analysis results is therefore improved. Besides 4 Unix libraries, the Abstract system also allows you to create your own user library for comparison analysis, contamination analysis, and value analysis. For more details specific on the feature abilities of Abstract, I would like to mention that Abstract displays total ion chromatogram and a traffic ion chromatogram on a single screen, and also allows you to subtract surrounding peaks from the target peak to obtain a high-quality mass spectrum. It also has ability to overlay chromatograms, extract ammo-resist ion. And one more thing that I like about Abstract is that the such next library is directly within from Abstract, and it is so convenient. I usually get questions such as, what application do you use for pyrolysis-GC MS? What kind of samples do you usually receive at the lab? And I would like to say that the application areas for pyrolysis-GC MS are broad. Materials used are closely related to our everyday life, from polymers, additive, plastics, coating, to biomass, energy, and related scientific. This chart is showing the materials and the corresponding application areas. For example, we could perform material characterization, quality assurance, deformulation of polymers. We could also analyze resin, plasticizers, films, UV antioxidant in plastics material, and so on. And that was all for my part. Now I would like to give my presentation back to Rosine for continuing.
Thank you very much, Atina. That was great. And thanks for sharing your tips and tricks and your experience with the Pyrolysis-GC MS. So now let me go into an application notes, as I promised, for material characterization and some failure analysis. So the first one is actually going to be directly on performing reverse engineering or deformulation analysis and performing failure analysis at the same time. All right. So polymeric products are often complex and frequently, as we know, include components from several sources and suppliers. The formulation details of the polymer parts are often not known to a lot of manufacturers. Actually, companies in a later stages in the supply chain may have even less information on components in a final formulation. So a same part number at a point in a supply chain can result in a polymer part that is not made with the same formulation, but the apparent polymer properties may seem to be the same. So after usage by a company or customer, a failure analysis may be required to identify the detailed chemical composition of the products. In this technical note, we perform material characterization analysis on 2 samples. As you see here, we call the good and then the bad samples. Both of the samples are diaphragms used in air pumps. The manufacturers likes to identify the chemical composition of each pump and also find the cause of the failure in a bad sample. The bad sample lasted less than 800 hours before cracking, while the good one lasted more than 1200 hours. And that was the definition of being a good versus a bad sample. So as we mentioned, your first step when you're trying to perform material characterization will be to use your evolved gas analysis mode of operation, EGA. So we did this. We performed evolved gas analysis as a first step. And these are the EGA thermograms for the good and bad samples, as shown here. On the top, you see the EGA thermograms of the good samples. At the bottom, they're for the bad ones. To perform EGA, we actually have a deactivated EGA tube. That's not a column because, again, EGA is not a separation analysis. EGA is a thermal analysis. So we had our EGA tube inside our GC that is directly connected from the injection port to the MS in our case. And we programmed the microfurnace from 100 to 700 C with a heating ramp of 20 degrees per minute. Also, I'm showing the results in triplicate here to indicate the reproducibility nature of the microfurnace technology. And as I mentioned, the temperature of the furnace is within plus or minus 0.1 degrees Celsius of the temperature of the sample. So you get consistent run every time. So by looking at the EGAs here, you'll see that the good sample has a relatively sharp peak at about 335 C. The bad sample has also a bigger peak than the good sample, but in a lower temperature zone. Also, the apex of the higher temperature zone is slightly different between the good and then the bad sample. So the apex is 490 C for the good sample and 498 C for the bad one. So even that 8 degree Celsius differences can indicate that the chemical composition of the samples are not the same. And before I'm going to show how we did more analysis, I want to mention that quickly by running evolved gas analysis EGA, which is a rapid screening technique, you can immediately figure out those two samples are not the same. There might be claimed that they have the same chemical composition or formulation, or they look alike, but you can immediately look at the EGAs and kind of include that they're not the same. Now, of course, you need to perform more analysis, such as separation analysis, to figure out the differences, but this is a rapid screening technique. So to analyze the EGA thermograms in more detail, we use extracted ion chromatograms that are called EICs. From the EICs here, so when we extracted, for example, 57, 55, 73 as EICs, we could also identify the optimal temperature zone to perform the hard cutting. And that's typically a good way of identifying your hard cutting zone by analyzing your EGA in more detail, which is trying to extract the M over Z ion that you're seeing from your EGA. So obtain your EICs and then try to identify a good optimal temperature zone for your hard cutting or flash pyrolysis, for example. Also, we found the optimal temperature for flash pyrolysis, in this case is 600 C for both samples. Now, if I didn't have my EGA thermogram, I wouldn't really know what would be the optimal temperature zone that I want to go after. So how would at what temperature would I program my furnace to thermally extract my additive? Or what would be the optimal temperature to run for my flash pyrolysis? But again, with running EGA, which is pretty quick, not that you can see there are differences between your samples, but you can also identify the optimal temperature zone. So to do that, to find the differences, now we want to perform some separation analysis using the flash pyrolysis and the hard cutting mode of operation. So to perform flash pyrolysis, or also as called single shot GCMS analysis, we change the EGA deactivated tube to now a separation column. And you actually do this switch using our vent-free GCMS adapter that allows you to do that without venting your MS. So it's pretty quick and efficient in your laboratory. And then we program the furnace at 600 C because, again, that's the temperature that we obtain from our EGA thermogram. Here you can see the flash pyrolysis pyrograms for the samples, the good one again shown on the top, the bad ones at the bottom. And as Atina mentioned about FSurge, we use FSurge libraries, which can include that both samples contain EPDM, ethylene propylene diene rubber, but you'll see that there is a small boxes, orange boxes indicate the differences between the good and then the bad sample. So still, by running flash pyrolysis, you could see some of the differences between those two samples. So we overlaid four of the pyrograms, two samples each in duplicate. And again, this is showing the reproducibility of the microfurnace design. Labeled peak number 1 and peak number 2 are detected in your good sample only, not in a bad one. And also the hydrocarbons are detected at around 18 to 22 minutes at a higher level in a bad samples. These are the MS spectra of two extra peaks detected, peak number 1 and 2 in a good sample, which are absent in a bad sample. Now, using FSurge libraries, peak number 1 is detected as the dimer that we expect to observe from chloroprene rubber, CR. And peak number 2 is a common fatty acid. So as Atina mentioned, FSurge is a polymer and additive search engine that focuses on polymer analysis and interpretation. And not only the compound is identified, FSurge also provides you with the possible source of the identified compounds. So once you integrate, once you analyze a peak, and FSurge will tell you that peak corresponds to this specific compound, also FSurge will tell you where that compound might be coming from. So what polymer that is, which when it's break down creates that specific pyrolysis in your sample. I'm just showing a screenshot of FSurge results. So this is the FSurge result, which indicates that peak number 1 is a dimer of CR. That also help us to interpret the origin of the pyrolysis and additives, as I just mentioned. And then for additional confirmation, the next step is to find the monomer of chloroprene rubber, because the presence of both monomer and dimer could be a very strong evidence that the good sample contains CR. So we did this. We did extract the M/Z88 ion, and this is, as you can see, the EIC, extracted ion chromatogram for the good sample. The chloroprene monomer and dimer are both detected in a good sample, but these compounds were not detected in a bad sample. So what we did was extracting 88 for both samples, good and bad, and as shown here, in a good one, you'll see pretty nice intense peak coming up in your EIC, versus in your bad one, they're not really showing up. So now we can confirm that at least one of the differences in chemical composition between the good and bad samples, it's about their polymer composition. And if you guys remember, when I was talking about EGA and how the apex was different, the good one was 490C, and then the bad one was 498C, even that is small amount of difference, 8 degrees Celsius difference, that was an indication of the difference in the chemical composition of the sample. So next, I'm going to show that we use the hard cutting mode of operation for more detailed deformulation analysis. Hard cutting allows the sample to be thermally sliced into sequential GCMS chromatogram taken from different sample temperature zone. And that's what we did at the beginning by analyzing EGA a lot more in detail and extracting different M/Zs to identify the optimal temperature zone for our hard cutting. Here is the screenshot of the Frontier Lab software for performing the hard cutting. The settings are very simple. A check mark is used to indicate the zones of interest for which a chromatogram will be generated. For example, the zone from 100 to 200C is not an interest to us, so there is no check mark here. So the sample, we're not going to sample that, which means instead of analyzing and obtaining the GCMS run for it, we actually going to vent it out and not using this. And by the way, we did not talk about system configuration, but you will need to have selective sampler and microjet cryo trap to perform your hard cutting mode of operation. So going back to the software, zone B is important for us because we want to know what is coming up in zone B. So we check mark the box for zone B, and that means that we will obtain a GCMS run for zone B, which is 200 to 300 C. So in this sample, 3 zones are checked. So the method will generate 3 GCMS chromatogram for each sample. And here are the 3 hard-cutting chromatograms for good and bad samples. The good one shown on the left and then the bad one on the right-hand side. So there are some differences between the samples, as you can see here. The different peaks of interest are labeled from peak A to F. And I'm going to show you the identification of these peaks in the next slide. But peak E and F are detected only in a good sample in zone D. The hydrocarbons are also detected in zone B in both samples, but the bad sample contains more hydrocarbons than the good one. And then the peaks in zone F are pyrolysis of the polymer. And we already kind of figure out the polymer composition because we already ran a flash pyrolysis. Now, if you would decide to not run a flash pyrolysis first, if you would only do a hard cutting, you could still figure out those polymer composition from your zone F of the hard cut. These are the library search results for peaks A through F that I just showed. Peak E and F that are long chain fatty acids are only detected in the good sample and not in the bad sample. So here is the summary table of the results for the samples. There are several clear differences between the 2 pump samples. Both samples are made of EPDM, but the good one also has chloroprene rubber, CR. In addition, the good sample contains palmitic acid and stearic acid as additives. So not only we perform deformulation analysis on the 2 pump sample, we will also be able to perform failure or comparison or even contamination analysis on the 2 samples. Now, using the same set of samples for additional analysis, we also did a PY-GC MS FID NPD, as I just mentioned, because again, that's important to say that yes, commonly the pyrolysis will be used by a GCMS technique, but it really depends on your application. And that's really one of the nice features of the PY-GCMS, which will be customizable to your lab and to your needs. So if you would need to go after higher chain hydrocarbons, you could use FID. Or if you are interested in nitrogen phosphorus compounds, you could pick NPD. So in this case, we use a detector splitter plate that allowed a parallel simultaneous detection by 3 of the detectors, MS, FID, and NPD. And again, NPD is for nitrogen phosphorus containing compound. So as you can see in this figure, the ratio is 1 to 1 to 1, and then the length of tubing to each detector must be correctly designed to achieve the correct ratio between each of these detectors. So this is the GC-MS FID NPD simultaneous analysis chromatogram for the good sample. The NPD detector detects some nitrogen and phosphorus containing compounds, and I labeled them here from peaks 1 to 7 at the bottom. They're labeled from the green color, and we'll show the peak identification of each of these peaks in the next slide. But as we saw earlier, the sample chromatogram includes a large hydrocarbon hump in about 16 to 20 minutes. It's very challenging to see minor additive peaks under this hump, even with the MSD. However, the selective NPD-GC detector observes several nitrogen and phosphorus compounds in that region since the NPD does not detect the hydrocarbon. This also allows some additional possible characterization for the sample. So here are the table, which is showing the compound identification of those peaks that I just showed from 1 to 7 using NPD detector, and then studied in the same retention time window with the MS. So each of these peaks contain nitrogen, phosphorus, or both in the possible structure as you see here. So it's really analyzing your sample in a lot more detail. Again, depending on your application, depending on your industry, if you're interested to go after additives that contain nitrogen and phosphorus, in this case, we use the NPD. So before we kind of have the webinar for question and answer, before that, I would also like to go over another application note pretty quickly. This is a short one, and this one is about reverse engineering of the epoxy adhesives. A little bit of background. Epoxy resins are a class of reactive polymers containing epoxide groups. A reaction could be based on either catalytic homopolymerization or even with a wide range of co-reacting, including polyfunctional amines, acids, phenols, and alcohols. Now, these co-reactants are often referred to as the curative, and the cross-linking reaction is commonly referred to as curing. And this results in a thermosetting polymer, often with favorable mechanical properties and very high thermal and chemical resistance of these samples. So epoxy has a wide range of applications, including the metal coatings using electronics or electrical components such as LEDs, also used in high-tension electrical insulators, paintbrush manufacturing, fiber reinforced plastic material, and a lot more, also including structural adhesives. So in this technical note, we are using hard cutting and EGA, so EGA and hard cutting mode of operation to perform reverse engineering analysis to identify the additive and also the pyrolysis mechanism of an epoxy adhesive. But before I go into detail of the app note, I like to thank and also I like to mention that this application note was developed by our good users at Case Western. And we actually have an application booklet about polymer processing with the collaboration of Case Western. So if you're interested, please connect with us afterward and we can provide a hard copy or electronic copy of the application to you guys. So to perform the experiment, we used an epoxy object and we actually, without any sample preparation or pretreatment, we cut a small piece of the solid sample. It was about 100 micrograms, and we placed it into the inert sample cup. I know Atina talked a little bit about sampling size, and I want to maybe point out a couple of kind of detailed information about the sampling size. It also really depends on the application and what you're trying to do. For example, if you want to do a bulk pyrolysis, then yes, we typically suggest somewhere between 50 to 200 micrograms because you don't want to overload your system. But if you're going after additives and coating on your sample, you could place a little bit more because you're not going to do bulk pyrolysis. So your polymers and your non-thermal active, the inorganic, will stay inside your cup. So in this case, since we're going to do a full analysis, including bulk pyrolysis, we only placed 100 micrograms. And the smaller the piece, the better in terms of homogeneity, and especially if you're performing quantitative analysis. So as we learned, first step was performing EGA to get a thermal profile of the sample. For the EGA mode, and again, remember we have our EGA tube in place and we program the furnace, in this case, 100 to 800 C at a rate of 20 degrees per minute. And then from the obtained EGA thermograms, as actually shown here, 3 thermal zones of interest. We call it A, B, and C were identified to perform separation analysis using the hard cutting mode of operation. So again, if you wouldn't have your EGA, you had no idea what would be the optimal temperature zone that you want to program your furnace for the separation analysis. So we did program the furnace using the optimal hard cutting temperature zone, and here are the hard cutting chromatogram for zone A, B, and C. From zone A, which was done from 100 to 260 C, a plasticizer was identified, and that's very expected because again, you are thermally extracting these additives and volatile using your TD, using the first zone of operation from your pyrolyzer. So instead of, as Atina was mentioning, any solvent extraction, you could actually thermally extract using your microfurnace and identify the additives in this case. In zone B, that was done from 300 to 420 C, a major peak of bisphenol A and also a minor peak of phenol were detected, which could suggest to us that its breaking of CO is dominated in this temperature zone, and also supported that the epoxy resin is a bisphenol A epoxy. And then zone C, which was the higher temperature, and I would call this a pyrolysis temperature zone, which was done from 420 to 550 C, carbon-carbon CC bond start breaking is more likely to happen here. Phenol, carbazole, and isopropylphenol were detected as major peak, while bisphenol A was minor peak. And also, alkali segment is detected, as I'll show in the next slide, which may come from the Hartner portion of the sample. So here is from zone C, the carbon chain fragments are separated by the number of carbon, and also the shortest chain comes out first. So from C5 to C17, all chains can be picked up by ion chromatogram extraction and distinguished by their mass spectrum. One thing I didn't show here, but I would like to mention is if you're going after higher chain carbon distribution, and if you would like to see heavy hydrocarbon, you could actually do that using your PyGC FID. And because the nice feature of the microfurnace where it's directly connected to your GC injection port, no transfer line, no dead volume, no cold spot, with FID you could see up to C100 from the pyrolyzer. So to summarize and give you guys some time to ask questions, here are some main reasons why you would need to add the microfurnace multifunctional pyrolyzer to your GCMS. So first of all, as I've been mentioning, you can perform multiple analytical techniques using multifunctional Pyrolysis-GC system. So yes, it's one instrumentation, but you'll be able to perform both thermal analysis, EGA, and also separation analysis. So thermal desorption, flash pyrolysis, thermal slicing, and a double shot. Also, this technology can be used for detailed material characterization, failure analysis, comparison analysis, and contamination identification. And I'm hoping with showing you guys a couple of real samples in the real world sample, you guys get a feeling of how this technique can be applied for these type of kind of contamination and reverse engineering type analysis. Also, virtually any material, including insoluble solids, can be analyzed without any solvent or sample preparation. And that's really a big deal for a lot of our customers when they have the pyrolyzer, the amount of time they save and the amount of samples that now they will be able to analyze in their laboratory. Because again, remember, as we talk, with adding the pyrolyzer to GCMS, you are broadening the range of organic compounds from gases all the way to the solid samples that are even insoluble that you could analyze by PyGCMS. And before ending my talk, I also like to mention, because I used to use FTIR and TGA in my previous role in conjunction with PyGCMS, I thought to mention that this technique is really complementary to FTIR. And as an analytical chemist, every tool has its own advantage, and every tool in your toolbox can actually give you answers. With PyGCMS, it provides a lot more detailed information on chemical composition whenever complete with IR. And also another thing is pyrolysis can overcome the challenges of peak masking for those compounds that observe infrared rays at the same or similar wavelength. And then lastly, critical for evaluation of unknown sample, the microfurnace performs a full range EGA, evolved gas analysis, actually from 40C over 1000C. And that correlates results to the well-established TGA, thermal gravimetric analysis technique, throughout the entire temperature range of the experiment. So I think I'm going to stop here. That's all I had for today. I'm going to turn the mic to Lauren, so hopefully we can answer some questions.
Awesome. And we certainly have some questions for you guys. Thank you guys so much. So I'm just going to dive right into it. But before I do, if you have questions for Athena or Rogine, type those questions at any time into the question module you see in the GoToWebinar control panel. We're going to do our best to get to all of them, time permitting. I know that there's a bit of a hard stop for our speakers, but if we don't get to your question, no worries. We will get back to you after the webinar. So let's dive in. First question, how does the double shot discern between additives and polymers, giving separate spectra for each?
So if I'm understanding the question, Lauren, the question is how the additives and polymers are identified. Could you read the question one more time, please?
Yeah, sure. How does the double shot discern between additives and polymers and give separate spectra for each?
I see. Okay. So with a double shot mode of operation, you actually will be performing two analyses on one sample. So as I mentioned, for example, once you perform your EGA, you know what's the optimal temperature zone for your thermal desorption. You program your furnace 100 to 300, cups drop into the furnace 100 to 300. On all the pyrolyses, all the additives, and all the volatile compounds directly will be deposited on your GC column. Cup go back up again in ambient temperature while your GCMS is running and collecting the data. So in your first TD, we call it TD thermal desorption chromatogram, that corresponds to the additives. And then once you perform the second shot, which means now you thermally extracted those additives and lighter compound, the cup again goes back for the second analysis, and that will be the leftover compounds in your sample. But when you do like 500 or 600 to break down those heavier polymeric fragmentation into smaller, more stable molecules, as I mentioned, pyrolysis, then using the F-search you'll be able to identify the actual polymers in your sample.
Fantastic. Next question. This one is for Athena. Since the audience picked up that you're new to PyGCMS, they wanted to know what's the most delightful thing that you've discovered about Pyrolysis-GCMS since you've become an active user.
Well, as I mentioned earlier, that I really like sample preparation using Pyrolysis-GCMS because, you know, the solid sample can be analyzed as is. I don't need to use any solvent, which take a lot of time, you know, for it take a lot of time for solvent extraction, and yeah, that was all the advantage that I enjoy a lot in using the pyrolyzer.
That's awesome. Yeah, thanks for sharing that. And then I think this one is for you, Rogine. If you could go back to slide 11, it's regarding the double shot. Do you drop the sample back in to go from 300 to 500, or do you drop it down only after the furnace hits 500? Let's see. Yeah, maybe it'll help to.
Okay, so slide number 11, if you
Yeah,
could please
slide number. Yeah, no problem. Regarding the double shot, do you drop the sample back in to go from 300 to 500, or do you drop it down only after the furnace hits 500?
I see. That's a good question, actually. So the double shot GCMS, the first analysis is a temperature program. So in this case, I did 40 to 300. The second one, to answer your question, it's an isothermal, so it's flash pyrolysis. In this case, will be 500. So with the double shot mode, actually, we call it double shot, but you have two TD runs. So you could have two temperature program, and then the last step will be an isothermal flash pyrolysis. But if you need to do, as you mentioned, for example, 300 to 500, that will be using your hard cutting mode, because the hard cut allows you to do up to 8 temperature program zone from your EGA thermogram.
Fantastic. This is a question. So there was someone who saw the toolbox on slide 14, and they are wondering, is this something that comes with a new system, or does it need to be ordered separately? How do they get this toolbox of good tools?
I guess I can take this one. Yes, you would need to order this separately. Although I want to mention that when you purchase the pyrolyzer, it comes with some consumables at the beginning, so like some cups or eco cups, as Athena was mentioning, for manual injection. But these are some tools that there are kits, and Athena is showing one kind of them. Actually, we have a couple of different toolkits depending on what type of sample you mainly deal with. So if you could connect with us afterward to say these are the sampling that I would need to do the preparation for, we have a specific toolbox for it, but it would need to be purchased in a separate manner than the actual pyrolyzer.
Fantastic. Another question is, how long does an EGA run take?
I want to share my experience, but then Athena, if you could also comment, since you're the one in the laboratory, depending on your method. Say if I want to do, for example, from 100 to 700, especially at the rate at fast you are using a ramping rate, say 20 degrees per minute. I want to say between 25 to 30 minutes, but again, it really depends on your GCMS parameters as well. But Atina, can you comment on your experience since you guys are doing a lot of EGAs in the lab?
Like it typically, like Rosine says, is really depends on the GC methods that you're studying. And for EGAs, I typically use I run the sample from 100 to 700 and ramping about 20 degrees C per minute, and it takes me about 30 minutes to complete the whole the run. And thermal resorption for EGA is have to really match with GC methods, so it's about 30 minutes.
Fantastic. Here is another question from the presentation. Rosine, can you go to slide 22 for me?
Sure. Here we go.
Yeah, can you clarify what EIC is again?
Okay, EIC is extracted ion chromatogram. So typically when you run your sample, you obtain a TIC, total ion chromatogram. And for example, these are TICs in slide 21 that I'm showing. But now when you extract different M over Z's, that will show you the EICs, extracted ion chromatogram, and that is shown on slide 22.
Awesome.
Is that clear? So for example, the green peak, as you see here, when you extract 57, that's going to be the peak that is come for 57, or 55, that's the black one, or so you are extracting different M over Z's for EIC.
Great. Awesome. Let's see, the next question I have here is for Athena. Athena, when you do a manual injection, how do you retrieve the sample cup from the pyrolyzer furnace?
How do you retrieve the sample cup from the pyrolyzer furnace? If it were for a single charge, you could use the eco pickup to get the sample, to get the cup out of the pyrolyzer furnace. But if it were for double shot, you would not drop the cup out of the eco stick that attached to the manual injector. So therefore, just simply taking out the manual injection and you will not need to worry about retrieving the sample cup.
Great. And then a question here for Rosine. What is the rate of pyrolysis? How does it compare with the Curie point pyrolyzer? And how does this influence the final results?
Well, I'm glad this is one of the questions because we really didn't go over the differences between different pyrolyzers. And by the way, Lauren, maybe you can mention this to our attendees that we do have a series of webinars that really discuss details about a microfurnace and its advantages, but I'm glad this question came up. So the time that is typically take to heat a sample to about 600 C if you're using the nitrogen and using the vertical microfurnace is about 100 milliseconds. Now, theoretically, by doing research, the time will be reduced to 1/7 in a helium atmosphere and is therefore comparable to the rate achieved when using a Curie point foil. But with the microfurnace temperature, as I mentioned, the temperature of the sample is precisely controlled to within plus or minus 0.1 degrees Celsius of the set furnace temperature to ensure that the sample-to-sample thermal profile is identical, so you have consistent runs. But in the case of Curie point devices, the temperature of the ferromagnetic foil, because they use ferromagnetic foil, increases instantly, but the contact between the sample and the sample holder is different in each run, which then reduces your reproducibility of the pyrogram. And then I know you didn't ask, but in case of the filament pyrolyzer, that's another category in the market. The sample position in a quartz sample tube relative to the filament coils is not the same in each run, so resulting in a poor reproducibility. So one thing you can take from this is with the microfurnace, your #1 competitive advantage in technology is the reproducibility and being able to perform quantitative analysis using the microfurnace.
Fantastic. looks like we have another question here for you, Athena. When a sample cup is dropped into the pyrolysis furnace, what stops the sample from spilling from the sample cup?
Thank you for your question. When the sample cup is dropped into the furnace, it is recommended that you use about 0.5 to 1 milligram of the poured glass wool to cover the sample, and this will prevent the sample from scattering.
Fantastic. And it looks like we have time for one more question. So, Rogine, I'm going to throw one your way. What is the difference between evolved gas analysis using the microfurnace and a headspace sampler?
I would say because the pyrolyzer is really designed to minimize the coldest spots in its flow path from the furnace to your GC injection port, because again, the pyrolyzer is directly connected to your GC injection port, you can analyze a wide range of compounds all the way, from low boiling all the way to the high boiling compounds, actually up to C40 when you're using the MS, and as I mentioned, up to C100 when you use FID. So the amount of sample required is several tens of milligrams, but the chemical species that are low as several as ppm and ppb can be analyzed using this technique. On the other hand, with the headspace sampler, based on my experience, they can handle several hundreds of milligrams of samples, but the thermal desorption of the targeted compounds, which are hiding inside the sample matrix, will be very challenging. And because the headspace sampling is, they're typically limited to 200 C, and the fact that most of them have a relatively long flow path from the sample heater to the GC injection port, compounds analyzed by headspace sample is generally limited to relatively low boiling compounds, typically up to C20.
That's great. All right. So we do have a couple questions left over, but you know what? Everyone, if you had a question that we weren't able to answer, my colleague Caitlin Heron will be in touch with you to make sure that we get that answered. So before we close up, I wanted to remind everyone about our next webinar on April 14th. During that session, we'll be discussing how modern benchtop elemental analysis tools are enhancing and streamlining polymer development from R&D to quality assurance and quality control. You will not want to miss this one. All right, big thanks to Rogine and Athena for joining us for today's webinar. As a reminder, as a registered guest, you're going to receive an email within probably the next 24 hours with a link to this recorded webinar. We encourage everyone to visit our resources page on lqa.com for future webinar details and to access our library of recorded on-demand sessions, just like that recorded webinar that Rogine mentioned called Simplifying Pyrolysis for the Modern User. That one is on there, ready to be watched. All right, everybody, thank you for joining us and have a great rest of your day.